Hello also from my side. So today we're going in the application field of maritime applications and focus a bit on using the base technology of printed circuit board embedding to form really robust sensor technology, which is really compact. And I like to go through you with the following table of contents. So first, I like to give a motivation, the demands on modern electronics, and then link it to the maritime systems. And also have a side note to cross correlations in production, which we see more and more these days. And then from that motivation, I draw the conclusion that we are a strong partner here in that field, and I will show how we can help in setting up complex production chains. And then I will focus a bit on one of the technologies because you will see we have a lot technologies to offer in-house, and it would be too confusing. That's why I will be around the focus of printed circuit board embedding here and give you also examples what we have already done or what we're doing at the moment in the maritime sector. So let's start with a quite simple image. For today's electronic systems, you can more or less find these four main parameters or main regions where you can optimize or work on electronic system these days. So beginning at the top here, that you want to have more and more compact systems. On the other hand, you like to increase the performance, but also have higher reliability and costs. And very prominent example is the smartphone you might all have. There you can see it's not only one of these key features that you like to optimize. You like to have it cheap. Like to have it small with high performance and also high reliability. So we are often more in these overlapping sections here. But you can see we have also systems in-house which focus more or less on one of these groups, like very small systems here, complete spectrometer on the tips of a finger, or components for high performance computing, or here a turbine sensor for very high temperatures. But that's more or less a general picture here. Let's focus a bit more on the topic of today, so the maritime sector. And there you can find more or less the same categories. If you can make the system small, you can have it at places where the water flow is of importance, like measuring in the water without turbulence. And a key feature is that you can have small housings. If you have these high pressures underwater, it helps a lot and saves costs for that. On the other hand, high data quality is also a goal you like to achieve because when you have high data quality, you are better in predicting things like rough waves, maintenance on offshore platforms, these kind of stuff. And what we also mean with high performance, not only supercomputing here, but with high performance computing, we also see in-house that we can package a sensor directly with a microprocessor, which is not a supercomputer, but you have a very small volume with computing power directly to the sensor and can so dramatically reduce the data rates you have to transmit, which is also a key feature on maritime systems. Even if you are underwater and have no direct cable link and you have to transmit, for example, by sound waves, then you need these pre-processing. And of course, reliability is a key issue in maritime systems. You have, of course, I do not have to mention it too much. You have the water, you have high humidity, which goes nearly in all organic materials. You have this salt or salt fog there. And additionally, not only these challenges here from the surrounding, you on the other hand have in most cases very high costs of maintenance and repair, which we see in offshore wind farms. And as an example, also made in-house here from our reliability department, which is also a good partner for reliability issues, which can be contacted. You see a complete molded power module. And this is it after exposing it several days to a very heavy salt fog. And you see even this molding cap, which you might see is very a very good protection, gives up at any point because there's organic material. The the salt will diffuse in that. And so I will show you later how we tackle this challenge here. And of course, the costs are always a driver. Even if you say, okay, the maintenance costs are this high, the cost of the single sensor doesn't mention too much. But if you can reduce the cost, you can make some of the sensor technologies firstly economically reasonably. But you can also add more sensors, or you get more sensors per euro, either way you see it. And that's where you have better chances to use the sensor technologies on an economically reasonable level. But you see another thing in the diagram. As I said, more and more systems are in these overlapping regions, and I think this is some kind of sweet spot, of course. Yeah, you like to have all in ones here, and that's why also the development direction for new systems mostly goes more and more in the inner part of this diagram, where you have these challenges in one spot. But this gives quite new complex problems, because if you look back doesn't of some couple of years, you have a production chain like this with the single steps in the green path here, and you do something like metal interconnect, and then you maybe check for the quality, and then you go to the next step. And the idea in that kind that you check between all the production steps is, at the end, if you have checked after every step, and every single technology, the system will be of good quality. But if we come closer with the integration technologies to each other, they influence each other, and there can be unexpected cross correlations. Now that you have a technique here, for example, that imprints critical temperature level or critical mechanical forces, and that will destroy the some components of the system which are manufactured much earlier. And we have made several investigations in-house. One example, maybe, which is quite visual here, is you might know from the power electronics. Here's a power electronics setup where you have a power electronics chip in the middle. It's wire bonded with heavy aluminum wires, and afterwards we have ultrasonic welded the terminals around it. And we could show in that publication that if you choose the wrong kind of wire and do the wrong configuration here, after even after 24 US ultrasonic welds here, you will break completely the bond wires. And that shows that there's a massive problem, that these technologies go closer together, and you will have a bigger problem if you buy these technologies or let these technologies develop at different companies or different vendors. And that's why a strong feature of the Fraunhofer IZM here is that we can develop complex systems with all necessary assembly and connection techniques in-house. So we can look for these cross correlations, and we know already a lot of, I think, a lot of these cross correlations, and can design the production chains in a fitted way to avoid these miserable effects. And as I said, we have all necessary techniques. I have this nice image from our from our press department, where they try to combine all the techniques we have in-house in one image. So it's a nice image to show what you can get at Fraunhofer IZM, and also it explains why I focus on one technique in this talk. But as you can see, we can starting from the wafer level, stacking chips there, routing chips there, then making interposers in the wafer domain, also making interposers with very high density fine line applications, also on the printed circuit board level. And we can add molding and underfilling technologies, also with shapes, put antennas on it, add optics to that, and not only optical waveguides in the PCB, but we can also, at the latest developments, switching to glass substrates. On the one side with optical channels inside, on the other side to address more fine line applications, also in larger formats. And we combine that also with groups in our institute who can make the system design for high frequency systems as a radar system here or antenna patterns for communication. So I hope that convince you that we have a lot of technologies and can combine these technologies to very complex production chains and also have the ability in-house to analyze failures and reliability issues coming even from production or at the usage of that technology. And now I will focus a bit down on the embedding technology and roughly speaking, it's printed circuit board, a printed circuit board technology in the base, but it's not this PCB technology which you can order and it's delivered after 24 hours maybe, because we also buy these PCBs if we just need double-sided PCBs, we also just place an order. What we do in house is we try to stretch a bit the technology boundaries of these technologies. We work on large substrate, like roughly 60 times 40 centimeters here. And we try to go to a line space that is more or less, I think, in a bridge region to the wafer level people. So we have also a department for wafer level stuff. So if you're looking really in the very small features which you like to have on your system, these are the right partners for that. But what we like to do is, or what we're doing since years, is also taking technology experience from that and try to port it to PCBs and have then line space below 5 micrometers on the very large substrates to reduce the cost. Large substrates is mainly driven by the wish to reduce the cost by producing a lot of systems in parallel. And when I said embedding technology, it's not only that we go to very fine line, what we also do in-house and what is very base technology for having electronics in rough environments is to place the components of the system inside the printed circuit board or inside the PCB. And as you see here, that's a conventional system. If you open your PC, you can see something like that. But what we can do here, we can place the components from the top in the inner layers. And now you might ask, okay, it looks fancy, but how does it help for systems? So if you do this, of course, you can make a system significantly smaller because you can place the components also in different layers. But you can also optimize wiring. If you have the ability to stack the components in a 3D manner, you can have very short wirings, which is very beneficial, uh, especially for high frequency systems where the path length is crucial. And we can also use here already tested commercial components, put it inside. So it's not experimental to put these components inside. We can use or we can select very reliable ones. And we have covered the entire system in one block, which makes it per design quite robust. By the way, what you see here is the image sensor, then it's the readout circuit. There is also a microprocessor that can extract image features from the taken recorded image and send it by USB, and that's all in that quite small block here. As I said, one of the main topics today is to make the system robust. And of course, if you have the 3D integration, one thing you get automatically is the system is smaller. You have to protect a much smaller volume, but you can also metallize the corners, or if what I will show later, we can nearly metallize everything around it. So we have a very nice EMC shielding. It's not only EMC shielding, especially in maritime applications. We use that metal also as a shield for water, because if you have somewhere organic, even in the epoxy, in the mold compounds, where you have a lot of glass and a bit epoxy, even there the humidity will go through. The only real good shield for keeping humidity outside your circuit is metal. And we can also combine that with the PCB technology here, or with the embedding technology. And as I said, you have this robustness. You have no components on the outside. You can play around a bit with the mechanical stress reliefs here also to make it really also the system a bit inertial against mechanical bending itself. I added this slide because if I show these slides before and show that we can embed easily SMD components in the inner layers, as here, I usually been asked if we also can work with bare dies, especially from people who work with telecommunication or radar applications, because they like to avoid any additional package because of signal losses. And yes, we can also do it. It's, as you see from the two schemes here, the technique used is a bit different. It has a bit different challenges, but we can do both, and we can also mix it in different layers. It's to form an entire system. And basically what we do is we place the component, either the SMD component or the chip, on a base layer, and then we cut out non-hardened epoxy layers here, fill it up, and then we laminate it as a usual PCB is laminated, so that we get a very rigid organic substrate with the electronic components inside. Here I like to summarize a bit the further emerging research topics we see, and which we will tackle at the moment or in the near future. As I said, these way of stacking in the 3D with this ability to have a very good reuse of the circuitry, because we do direct laser writing of the masks here, so we have no masks. We direct laser write the lithography for the lines, so we can or have very short development cycles. And as I said, we have these short lines also from the chip to maybe in patch antenna pattern, which is shown in that graph here. And that's why these systems are very beneficial for 5G, 6G, or whatever you call the next generations afterwards. Either in communication systems or radar systems, and there we can also work in these materials, which is not the standard FR4 material. We have some specialized materials which also can or have very good dielectric properties, even above 120 gigahertz here. So we can make ultra compact packages with also including maybe phase shifters, so that you can also arrange it in an array and have very nice communication systems also for the high frequencies. Another main topic we are in is power electronics, because there we can use the ability to provide thermal path also in around the chips, that we have very short ways for the currents to flow, and reduce the impedance, especially for very fast switching circuits. That's why we have a lot of projects in the range of DC-DC converters and AC-DC converters. And we also either we make it quite big, like this one here down in the corner, which is a 50-watt module, which is embedded. But we also go for very small modules, which can be distributed either also in computer networks, which you might use for cloud computing or directly in data centers. And as I said, these housing, I will also emphasize it a bit later, that these housing is very beneficial also for the maritime applications and also used extensively by us. And of course, if you have the ability to package a sensor close to a microprocessor, you can imagine that it's a big field of so edge cloud sensing, that you have a sensor unit and you can add, for example, AI accelerators to that to do pattern recognition right at the sensor and just transmit the data on a very short latency time. That's the topics we are looking into. And now I like to come back a bit to these image for the maritime systems, and and I go through these aspects now. with some examples from maritime projects. I think that's always the best that you see that we have, or how we have realized it in reality. And the first project, which we do together with the group for the gluing and underfilling system here in the house, is called deep sea protection. And you see the partners here. It's a quite large project funded by the German Ministry of Economics and Climate. And what we do here, we like to build sensor systems which have high resolution for a survey on the sea floor, but also on the way to the sea floor, so all the way down to 6,000 meters under the water level. And it should be specialized on either the geographical survey, but also on organisms, and also to find obstacles, for example, if you want to place some infrastructure there. Of course, if you have a good map, it helps also in mission planning. So we like to also go directly to geo-reference maps in that project. We of course like to protect also areas either for biotopes, or you can imagine a critical infrastructure is a quite hot topic today, to protect them. And of course, if you have sensors there, you can also optimize production support. You can have inline technical inspections, for example, of pipelines or important data cables. You can analyze the biotopes, the sea itself. And of course, we hope to generate a lot of interesting data also for the next years to evaluate with that sensors we can place there. And there are a lot of tasks in the project, but the specific task for Fraunhofer IZM we're working on is the very small and pressure neutral electronics for mainly two of the components. They call it manta, which is a like the fish. It's a movable vessel that can move through the sea at high depth, and also they call it calma, which is some kind of signal buoy, which goes up down to 6,000 meters, which is enormous pressure. And what we do for them, especially for the movable thing here, is a navigation system packaging. We also package the sensor technology for both. We, especially for the manta, integrate the coordination of the movement systems. So you see the propulsion of the manta is made by these kind of wings that need some powering up from the batteries. So we also work on the power electronics for that. And last but not least, the data transmission, especially if you have something that is swimming freely around. And here we find the concept, or the challenges I've mentioned for PCB embedding again. So in the conventional setup, you have to have a shielding housing for that, and you have often this stack up of PCBs where you just have the rerouting layers in the PCBs, but all components are on the top. And to make it possible to go into high depth with that, you have to fill it with some material, because if you have air there, the air will just crack the system and it will burst. And as I said before, these challenges can be tackled very nicely by the PCB embedding technology, because we have no air bubbles inside. We have a solid block of material which is functional because we have these components inside it. So we have a high reliability, and we get additionally these optimized wiring for better performance. And also the system is much smaller in volume and weight. And the aim here in the project is that it's pressure resistant up to 16 megapascal, and the reduction compared to the state-of-the-art system in volume should be 50% and 60% in weight. And this project is, by the way, it's it's a bit more on the application side. You see here, we like to bring the technology readiness level to 6 in the project. So it's not a basic research project anymore. So we want to go to really technical demonstration with that, also with the knowledge of some earlier projects where we develop modules for deep sea. And just to show that we really can do it, because up to now it's just a PowerPoint engineering. We have already realized some of the key modules, and usually we start with a circuit diagram and we develop it usually with the partners who likes to have the functionality. And then usually this circuit diagram is built up in the first stage in a conventional PCB, just as top mount to check if it works. It's debugged then, and if it works, we do an embedding design. And you see, these are the multi-layers in different colors here. And at the end, it looks like this on the right side, but it looks always a bit like a PCB, and you could not see what's inside. That's why I have here an image of an inner layer, and you can see we have placed the components here, and these components will then be surrounded by material and laminated in a step, so that we have a compact block at the end. And you see it's quite small. Here will go, I think, here will go a battery in that case. And this is for the steering system for the Manta. And on the other hand, we have here the example of the power electronics for the drive system. And if we talk about power electronics, we have much more copper in it, because we control here higher current flows, and we need the copper also to cool down the system. And there we also use techniques as silver sintering here, for example, to contact the power electronics closely to the heatsink. And you see, as I said, the finished module always looks like some kind of PCB, because you could not see the components there inside. So, and as I said, we are also working together with our group for encapsulation technologies here in-house. And if we have some components which must be placed on top here, like sensor units, which makes no sense to place some of the sensors inside, if they have to have direct contact with the medium they measure, we can add another technique to the PCB, that is to use epoxy-based materials for encapsulation here. And we can also make sure that they are bubble free, because, as I said, under these high pressures, up to 6 kilometers under the sea level, we have really high pressures, so that any air bubble inside would cause problems in the system. And therefore, we have their pressure cure processes in-house that can make sure that we have no gas remaining. And then afterwards, we can also use direct metallization also on top of these materials to avoid the humidity going inside, and to avoid the need of a special outer housing of it. And to show that it works, to protect it from humidity, there were some measures. Here are some. There's a very optimistic scenario which was simulated. That's the bad scenario, and we have shown that we are really good in that corridor. So we perform quite good here in the absorption of water over time. You see here 2 days. But you might think, okay, that's quite okay for a system which I put in water and have maybe for a day, half a day, or 2 days in the water, then it's okay. It will make no short circuits. It will cause no big corrosion inside it. But we had also another project, so I switched to the project we called eHarsh, and it was a Fraunhofer internal project with these institutes I mentioned here. And there we had the challenge that we have also really high temperatures, which you normally maybe not everywhere at the sea ground present, maybe also only in the thermal active regions. We have also very high pressure as 1,500 bar, and we have very heavy corrosive salt solutions. and it was made for geothermal projects where you have where you drill large holes and you have some salt water in these holes also to monitor and to wash out. And there it was not enough just to seal it a bit. There we developed a technology where you have, and you see it here in the principal cross section, these orange layers are metal, and the metal completely surrounds the PCB. So, and you see it on the realized samples here, it's completely surrounded, and even at the regions where we separate the modules out, we have just metal, that we have no open organics here. We just cut through the metal and have a complete hermetic sealing. But you might then ask, okay, if you have a complete metal sealing, it's quite useless because you even cannot contact the inside. You get no information out. That's why we had to figure out how to make also very robust contacts, and therefore we here with the colleagues from the Crystal or Ceramics Institute in the Fraunhofer group, we developed these contacts which are based on ceramics with a metal frame and have these metal contacts in the middle. So we used these as contact lines on top, and we finally were able to produce modules for power applications. These are the power units, which gives the current levels we need. These are the sensor units with a bit more contacts here and with the sensor opening there. And they in the lab, they withstand these conditions. And now I've talked a bit, or now I've talked longer about these very high depth, it's very high pressure, but we have also at the moment a present project together with the Fraunhofer in Bremen, the IWES, and the Fraunhofer Institute for Communication here in Berlin, the HHI. And there we looking in technologies for offshore wind parks. And I think as you might know, offshore wind energy is a very increasing market because the regions on land where you can place wind farms are limited. And on the other hand, the conditions to make energy from wind on offshore sites where you have strong winds, where you can place larger systems, is quite a good idea from that point of energy generation. And this is the plan or the development goals here in Germany, that we increase it significantly in the next decades. And one big challenge we tackle in this project, I like to mention here, as you might also have seen here, that we built the next generation seismic streamer. And what does it mean? As you might see here, you have these offshore wind turbine, but this wind turbine has to be put in the ground somehow. And this is the quite expensive part on that, because you have to know what is there, because then you can make the best choice for putting this basement here. And to do this, you have to look in the ground in the first 100 meters. And what is also done today from the technical side is that you have this streamer, and the streamer is more or less a chain of microphones, which are for these surveys is up to 500-meter long, and you have a sound source there. It makes a loud noise every second. The sound waves travel into the ground, are reflected if the ground layers change, and this is recorded by the microphones here in this microphone chain. And at the moment, these systems are present, but they came from the oil industry. And the oil industry is not interested in the first 100 meters. They're interested in depths of 3 to 5 kilometers or more. That's why they have systems which has rougher resolution, because they're not interested in finding a small oil bubble. They're interested in larger structures. And they are much longer because they have to evaluate the signals coming from larger depth. That's why there's there's a big need for such a system, but it's quite complex, and that's why we do it together with these institutes, make a prototype of a new system, because for the industry it's quite hard to come up with such a complex solution, because they tend to use that what they get from the oil industry and try to tweak it a bit, but it doesn't help too much at the end, because it comes up with new problems. As I said, at the moment, they have the biggest problems that they have limited data rates, because they do all the data aggregation at the boat. They have the problem that their sensor spacing is too large. As I said, they are built for finding larger structures like oil reservoirs. That's why they have an insufficient resolution in both directions. So they are not made to find here big boulders, which can inhibit building or make building a base for wind turbine quite challenging, and that's what we like to do. And the other thing, which was also new to me, because I didn't think before the project into that topic, is there's always a compromise in the towing depth. If you tow the streamer lower, you have a big advantage that you have no influence of the wave, because the wave goes 1 to 5 meters deep, the wave motion. But when you tow these microphones too deep, you get from the sound wave, which comes from here, you get a reflection on the water surface, and it comes back and hits the microphones. And these microphones they use today are very very sensitive, but they have no direction characteristics, so they don't know where the signal comes from, and this is also a big problem for these systems. And our approach roughly is, of course, to reduce the sensor spacing. So we will have microphones every half meter in the system. We will have more microphones with the direction characteristics, so that we can distinguish from where the sound comes, so that we have a higher resolution. Also in detecting some boulders there. And another thing is that you have that's more or less a hose with the microphones inside it. And here's it's nicely straight drawn from the ship, but in reality, it is roughly in one line. It's more a bit bent. And of course, if you want to detect something that is a meter a large boulder, or half a meter large boulder, you have to know the position of your microphones with high accuracy. And that's why we are also working on shape detection. We will place inertial measurements units in every sensor unit, and we will also have a fiber-based system for shape sensing of the streamer. And we get a lot of data. We get something like even from one streamer, and in reality, uh, a couple of them are drawn in parallel from the ship, and we will get some like 8 gigabit per second maybe. And to transfer that, we also develop data aggregation units which pack the data in the streamer. And that's also new, that we also place much more electronics. We place the digitalization of the data in the streamer to have higher data quality. And that's quite challenging. And we have to use all these considerations I've shown in the projects before. And what we are already now building up and have constructed and tested, and it's in the last qualification steps, is a DC-DC converter. It might seem simple that you need to have the power somewhere, and you might be surprised that we go from 120 volt to 3.3 volt for powering our ICs. But we calculated it also for lower voltages, like 60 volt you can take, or 48 volts, which you know from automotive. But if you go lower in the voltage, your cable diameter, which you have for the bus bar here to support all the systems, gets bigger and bigger, and it adds so much weight to the streamer that it will simply sink. So that's why we have to build, and it's quite challenging to build a DC-DC converter, which makes these large step and make it small, because the streamer has a diameter from 3.5 to 4 centimeters in the inner side. So We managed to build these converter which can deliver 12 watt for the FPGAs we need for data aggregation, just on a footprint of 3.5 centimeters here. And you see a lot of wires here, and these are for the IMC shielding. And we have still the option to cover it here completely with metal if we get any problems with the humidity. So I hope you enjoyed a bit this travel through our maritime projects. And I hope that I convinced you that Fraunhofer IZM is the right partner for any development of complex electronic systems, because we have this technology in-house and we think that we have a good understanding what are the cross correlations between the technologies, and can also set up different process change for the same module, and also look which is the best solution also for the customers, and then also transfer it to partners where we know that they can also produce it and that you can order it from them. I hope I've convinced you that we already have experience with the challenges in the maritime environment here. And as I said, we have a lot of technologies in-house, so I just focused on the PCB embedding and a bit around it, but there are much more. We have a group that deals with flexible systems. We have an optical group. They do the glass housing, which is also nice if you like to have optical systems underwater, and they can also build up very small optical systems, very small spectrometers or sensing systems. We have groups here in-house who can design communication systems, radar systems, and we have the great opportunity at Fraunhofer IZM that we compare all that. We can combine the packaging technologies, and we combine the ability to design systems also with you, I hope. So that's, I think, all from that talk. Thank you much for your attention. And here are my contact details. And if you have any questions, do not hesitate to ask now or send me an email later.